So this will be a longer video, but it will go one by one through the minerals that will help you kind of prepare for your first mineral test and see which are the properties that are most important to remember when you're identifying each individual mineral. Feel free to skip through this to focus on the minerals that you've been struggling with. And I'm going to go kind of through one by one, talking about how I find it useful to identify different properties of minerals that help me focus on a name. So let's start with mineral 1. Mineral 1 you can see is here. Mineral 1 is sulfur. And honestly, I'm not going to spend a ton of time on sulfur because the most identifiable property of sulfur is its bright yellow color. Sulfur it does smell, but that's very hard to tell in a virtual world. But nevertheless, it has no cleavage either, because it's just kind of shapeless and lumpy. And it also has a non-metallic luster because it's not silver or gold in color, which is not the case for mineral 2. Mineral 2 is silver, and mineral 2, therefore, is metallic. Mineral 2 also is incredibly soft. So what you'll see here is that mineral 2 can very easily create a silver streak on a streak plate. Mineral 2 also will come off on my fingers. That's because mineral 2 has a hardness of 2, and it is graphite. It is the same graphite that you have in your pencils, and that's why we use it to mark on paper, because it is so soft that it will just break apart as soon as we apply any pressure to it at all. So there's also no cleavage in mineral 2. You can see that it's just kind of lumpy in shape, without any sort of perfectly flat sides. So mineral 2, graphite, metallic, soft, and no cleavage, which is different from mineral 3. Mineral 3 is galena. How do you remember galena? Well, first of all, it's very dense and heavy. That's because it's made of lead. Galena's chemical formula is PbS, which means 1 atom of lead and 1 atom of sulfur in each crystal of galena. Galena, you'll also see, has this perfect cubic shape. Well, not perfect, but it's a cubic shape, which tells you that there's 3 directions of cleavage. One direction of cleavage you can see here is the left and the right, where you have flat parallel sides. This is one direction. Second direction is the top and the bottom, where you have flat parallel sides. And the third direction is the front and the back. Now, if you look, these 3 sides intersect at about a 90-degree angle. That's why it makes a little cube shape. And if you can look at the broken chunks here, you can see that they've also broken off in little cube shapes. So this idea, cleavage, is the idea that there are weaknesses in the crystal plane, in the crystal of this mineral, and that when you break it, it breaks along those same crystal planes, those same angles every single time. So every single time I break galena, it should break into a cube. That's one of its very identifiable properties. There's also a lot of cleavage in mineral 4. So much cleavage that you probably won't be able to identify it, honestly. Mineral 4 is sphalerite. It has 6 directions of cleavage. How do you remember this if you cannot find all 6 directions? Well, what you remember is that sphalerite is black and goldish in color. And you remember that it has a lot of perfectly flat sides. And all of those flat sides are different planes of cleavage. And honestly, that's how I remember sphalerite. It has kind of a yellowish streak, but for me, the black and gold with all of the flat sides for all of the cleavage is enough to remember it. So cleavage is not important in telling the difference between minerals 5 and 6, but hardness is. So people frequently confuse minerals 5 and 6. They look pretty similar, right? They're both metallic. They're both gold in color, but you can see a couple things that are different. One is very easy to see, and another takes a little bit of work. So mineral 5, you can see, is a little bit more goldish in color than mineral 6. That's because it has copper. It gives it that coppery color, more like a penny, I guess. So it's a brassier yellow than mineral 6, which is more of a pale gold. So this mineral is called Calcopyrite. Mineral 5 is Calcopyrite. 6 is pyrite. Calco means copper. And so that's why this is Calcopyrite. It's pyrite with copper in it. And pyrite is just iron and sulfur. A lot of times people call pyrite fool's gold. And I'll show you how you can tell that it's not gold as well. So the big difference between Calcopyrite and pyrite is their hardness. So here's a glass plate, and not only can you see scratches on a glass plate, but you can also hear them. So if you scratch Calcopyrite, nothing will happen because copper is soft. That's why we use it in wiring, because it's bendable and it's not particularly strong. So you'll hear nothing when I do this. Nothing. Pyrite, however, is a little bit harder than glass, and so you'll be able to hear it when I scratch the glass. So that sound, which is almost like a nails on a chalkboard to me a little bit, that sound is the pyrite scratching into the glass, because pyrite has a hardness that is greater than 5.5, and Calcopyrite is softer than 5.5. So that's the big way you tell the difference between the two of those. So mineral 7 is also harder than glass and much harder than glass. So that's one of the ways that we remember corundum, which is mineral 7. Corundum is harder than glass, which you just heard there. Corundum is also distinctive because the way you'll see it, it's always in a 6-sided hexagonal crystal. So that means when you have a mineral and you can see 2, 4, 6 sides in a long crystal like this, and it's harder than glass and it's kind of opaque, that's corundum. So gemologists use corundum as an ore for sapphire and rubies. So the only other mineral that you'll see that's sort of hexagonal like this and harder than glass is quartz, which we'll get to later. But what you can see is that quartz is transparent or translucent, and meaning that you can see through it, even sometimes poorly. But that corundum is opaque, meaning you can't see through it. So corundum, very hard, hexagonal crystal, and you can't see through it. All right. There are 2 examples of basically the same mineral for minerals 8 and 9. They're both called hematite, and I'll show you why. But hematite has a chemical formula of Fe2O3. That's 2 iron atoms and 3 oxygen atoms. And when iron reacts with oxygen, it produces rust. So mineral 9 is what iron looks like prior to rust, to reacting with all that oxygen. And mineral 8 is what it looks like after. So how can you tell that these are the same mineral? They look very different. We can see that they both have no cleavage because they're just kind of lumpy in shape. Although you can see that mineral 9 is silver. So therefore this is a metallic variety of hematite. Mineral 8 is a non-metallic variety. The way you can identify that these are both hematites is with their streak. So on the streak plate, I'm going to show you that mineral 8, oops, there we go, produced this reddish orange streak right down here. Mineral 9, even though it's metallic, also produces a reddish brown streak. You'll see there's some silver flecks in there as well, but to brush those away, you can see that, again, reddish brown streak for both minerals 8 and 9. And that is because hematite, if you think about the word hema means blood, like blood red, like the streak. Whether you're thinking about like a hemophiliac or hemoglobin, hema is the word you're looking for that means blood. Another metallic mineral we see in number 10. And it's a little bit more challenging to identify number 10 as metallic because it is, it's silver, but it's not quite as shiny as some of our other metallic minerals. However, what number 10 has that no other mineral has is that it is strongly magnetic. And that's the only mineral that you have in your set that is strongly magnetic. So it's a really easy way to identify magnetite, which is sample 10. Okay, so mineral 11 is limonite. Limonite kind of looks like it's been through some stuff. It is sort of a rusty color. A lot of times limonite looks like it's beat up and kind of weathered, and that's because limonite largely forms from the process of weathering. And it absolutely has no cleavage. You can see it's mostly shapeless. It has one random side, but that side doesn't reflect light back at all. So this has fractures, 0 directions of cleavage. And the other thing about limonite is because it is the product of weathering, it has a really variable hardness. Sometimes, like that chunk of limonite scratched very well, but they don't always scratch well. However, what limonite does have is a distinctive streak. Not when you pick a really hard core though. Okay, so here is limonite's streak. You see that it's sort of a yellowy orange color, and that is pretty characteristic of that mineral. So that's how I identify limonite. Let's keep it simple as we keep going here. So here's mineral 12. Mineral 12 is halite. Halite is salty. It tastes salty, which again is hard to do virtually. But what you also see is halite is another little sort of rectangular prism, which means that it has cubic cleavage because it has 3 directions that roughly come together at 90 degrees, like boop, boop, and then boop. So here's our little cubic angle. And so this one isn't perfect. And the reason is because halite is very soft and it's soluble. So it'll dissolve. Even if your hands are sweaty, you'll get halite begin to dissolve, which is not the case right now, in case you're wondering. So there's a lot of white minerals. Halite is really the only one that breaks into cubes, and it's the one that tastes salty, which again is not useful for you. All right, we skipped mineral 13 and we move on to mineral 14, which is fluorite. Fluorite is also like quartz. It can be a ton of different colors, but what's distinctive about fluorite is that it has these little pointed edges in fluorite where you basically have 4 directions of cleavage coming together. You'll also see that very often you'll have like a point right here where you have 1, 2, 3 sides coming up. And a lot of times, a lot of your points will have like a very small side because fluorite frequently cracks sort of in a variety of ways. But regardless, you'll find a side where you have 1, 2, 3, and then a 4th flat side. So fluorite has 4 directions of cleavage. You want to think F for 4, F for fluorite. That's probably useful. Fluorite tends to form little pyramid shapes. Sometimes it forms a pyramid on top and then a pyramid on the bottom, and it forms a little octahedron, which is cute. But fluorite is also softer than glass. And so sometimes people will confuse it if you just see this part for quartz. But the difference is quartz is harder than glass and it has a hardness of about 7. Fluorite, softer than glass. So that's how you tell that apart. Oh, look, another white mineral. This is mineral 15, which is calcite. So calcite can actually be a ton of different colors. But how you tell the difference between calcite and some of the other light colored minerals that clearly have cleavage is that calcite reacts to acid. So the way that looks is, I'm going to name it a paper towel. If you take a drop of hydrochloric acid, you put it on the calcite, you'll see bubbles. So the chemical formula for calcite is calcium carbonate, which is CaCO3. And all of these little bubbles here are carbon dioxide bubbles. The carbon dioxide has been liberated from the calcite crystal when I apply acid, and then I dry it off because otherwise it'll eat through my sample. The other fun fact about calcite is that while it definitely has 3 directions of cleavage, similar to halite, what's different is that calcite is a little rhombohedron. It kind of looks like a rectangle that's been pushed over on its side, and it forms 60-degree angles. instead of these nice cubic angles that we see with halite. So halite, 3 directions of cleavage, cubic cleavage, and calcite, 3 directions of what we call rhombohedral cleavage because it forms a little rhombus. And also calcite reacts to acid. Calcite is the only mineral that reacts to acid, which is very important as we study rocks in the future. Okay, another cute little rhombohedron is number 16, which is Dolomite. So Dolomite, this particular sample is dark colored, but Dolomite can be any color. It can be pink, it can be yellow, kind of a cream color. This is an example of a dark colored Dolomite. And again, you'll see that this Dolomite forms a little rhombus, which is 3 directions of cleavage that are not at 90 degrees. They're usually at 60 degrees. And what's fun about Dolomite is that if I put acid on Dolomite, nothing happens. So until I take my little glass plate, I'm going to create some Dolomite powder. So on that powder, I can then put some acid. And the powder will react to acid. And that has to do with the chemical composition of Dolomite, which is not super important for our purposes, but there's magnesium that is stopping the calcium carbonate from being liberated. So you got to break up that magnesium so you can get to that carbonate to free the carbon dioxide, which is not necessarily something we want to do as humans. We produce plenty of carbon dioxide, but I digress. Let's move on to mineral 17. Oh, look, another white mineral. This one is called gypsum. And gypsum is softer than glass. You can scratch gypsum with your fingernail pretty easily, but one of the distinctive features of gypsum is, so again, these are non-metallic. There's one direction of cleavage. You can kind of see as I turn this over for you that this side of gypsum will reflect light back to you pretty instantly. All at once, the whole crystal face lights up and bounces light. What you'll frequently see with gypsum is that it is layered on the side. And that's because gypsum forms when seawater, or actually just when lake water evaporates, it'll leave behind a layer of gypsum very frequently. So there's layers because literally each one of these layers was deposited as water was evaporating from a lake, and it left behind gypsum, which is calcite, some sulfur, and some sulfate really, and a little bit of water. So in summary, gypsum, softer than glass, one direction of cleavage, layered. Mineral 18 is another 6-sided crystal, and this is a hexagonal crystal. So something I forgot to mention with mineral 7 is that just because something is in a hexagonal crystal does not mean that it has cleavage. In fact, it means it has no cleavage, because cleavage means that it will form that shape when it breaks. And a crystal only grows that way because there's room for it to grow. So apatite has no cleavage, just like corundum, which was number 7, has no cleavage. I'll show you this a little bit more obviously when we get to quartz, where I'll show you that sometimes quartz grows into these crystals, but a lot of times it doesn't. So how do you tell the difference between apatite, which is kind of this greenish crystal, but apatite can be blue and apatite can be pink and a whole bunch of other different shades. How do you tell the difference between apatite, which is number 18, and corundum, which is number 7? It's a hardness thing. So remember, corundum has a hardness of 7. Apatite has a hardness of 5. And so it won't scratch glass, but it'll get darn close, but it won't. So I wasn't actually scratching the glass there. I can see that it kind of sounded like it. So I'm going to pick a cleaner spot. All I was doing was rubbing it in some of the grooves where the glass had already been scratched. All right, so that was a quieter sound. It was more of a rub than a scratch. So apatite, softer than glass, but still a hexagonal crystal, still with no cleavage. Another mineral that is frequently green, because apatite is number 20. Number 20 is olivine, and olivine is olive in color, really, right? It's green. And the other thing you'll see about olivine is that it very often occurs and like these grainy granular masses. It looks like green sand. Olivine is the main mineral that we find in the mantle of the earth, and it's also iron rich. Sometimes iron is green and sometimes it's red, and here we see some green iron. So honestly, olivine is like olive colored sand, and then you keep it moving and you go on to number 21. So our next mineral doesn't really come up super well on camera, but this is garnet, number 21, and it is this deep red color. So what you'll notice about garnet is that it has something that we call fracture that resembles cleavage. A lot of our garnet in this lab came from New York State in the Adirondack region, which is pretty heavily metamorphosed. And so there are a series of flat sides that actually just represent where the rock was sort of compressed during continental collision. And so you have a lot of these flat sides that kind of look like cleavage, but are not. And the clue that they're not cleavage is that the sides don't really reflect light very well. They just they have a dull sort of luster, almost like a resinous luster to them. And so the way that most students identify garnet is that it's always this characteristic deep red color. Now, in reality, it's not always this deep red color, but in 101 lab, this is the way you'll see it. So deep red color, this is also slightly softer than glass, and no cleavage is garnet. All right, so speaking of cleavage, samples 22 and 23 have cleavage that doesn't follow our normal rules for cleavage. So 22 is augite and 23 is hornblende. So there's a lot that's similar between augite and hornblende. They both kind of just look like the most basic rocks you can imagine, but neither of them are rocks, right? They're minerals. What's different is that augite breaks into this sort of characteristic blocky shape. And on an augite sample, you can always find a perfect 90-degree angle, like right there, where you have a very flat side here and a very straight flat side here, and they intersect at approximately 90 degrees. So this is considered, even though there's not like necessarily a set of flat parallel sides on both sides, the way we do have on other minerals, this is considered two directions of cleavage that it meet at 90 degrees. And augite and hornblende are both just slightly softer than glass, and they are both black in color. And hornblende also has sort of an odd cleavage pattern. And hornblende cleaves in two directions that meet at 60 degrees. It always kind of forms a horn. So you'll see like a 60-degree horn in every sample of hornblende. The other thing that you'll see is that hornblende is characterized by having these long, narrow crystals. And when you see hornblende in igneous rocks, which you'll see in a couple of weeks, you'll see just these small little slivers of hornblende where the hornblende has, as it's forms these 60-degree angles, these two directions of cleavage that meet at 60 degrees. Neither of these react with acid. They're both non-metallic and dark colored, and they both don't follow normal cleavage rules. So that makes them a little tricky, but honestly, remembering the habit of hornblende to form into those narrow crystals really does help quite a bit in its identification. So speaking of minerals that are often confused, 24 is your sample of kaolinite, 25 is your sample of talc. And folks always want to call kaolinite talc because it reminds them of baby powder or talcum powder. But in reality, kaolinite is this really chalky mineral that just has an incredibly low hardness. So does talc, also have an incredibly low hardness. But kaolinite is characterized by this chalky texture. In fact, kaolinite is the main ingredient in the medication kaopectate, which is basically an antacid that coats the inside of your stomach with chalky medicine to absorb and react with the acid if you have indigestion. Talc, even though everyone likes to think of talc as baby powder, and it is the source of baby powder, or one of the sources. That's only after it's ground down considerably. Talc, while both of these are much softer than glass, softer than your fingernail, what you'll see is that talc often has some gold flecks in it, and it's more crystalline for sure than kaolinite. So again, kaolinite is the chalky one. Talc is a little more crystalline and often has some goldish color to it. Two minerals that are not often confused but are very similar because they're in the same mineral family are number 26 and 27. And sample 26 is muscovite. It's called muscovite mica. They're in the mica family. And 27 is called biotite mica. They're similar, right, in that they both have one direction of cleavage. This sort of like left-right, this is one direction of cleavage. And they're also similar in that they break into thin sheets, and this is actually something I did in a previous recording of this video with my muscovite sample. They just simply peel off. So this is cleavage, right? This is the idea that when you break something, it breaks into the same shape always. That's what cleavage is, along weak planes in their crystal structure. So the light colored one is muscovite, the dark colored one is biotite. And the reason that there are these two different shades is because muscovite is primarily made, it's a potassium aluminum silicate. Potassium and aluminum are lighter metals, so you get this lighter color. Biotite is a magnesium iron silicate, so you get the darker colors with those heavier metals. So I would say this is a crowd favorite. Our samples 28, 29, and 30 are all samples of quartz. So you can see that here we have three different examples of the color that quartz can be. It can be clear, like we see in 28, which is quartz crystal. It can be white, like we see with this milky quartz, which is 29. Or it can be pink, like we see in rose quartz here, which is number 30. Beyond this, quartz can be pretty much any color. It can be blue, it can be purple, and then we call it amethyst. It can be orangey yellow, and then we call it citrine. So quartz has holes in its crystal structure that allow for lots of different impurities, and those impurities result in the different colors of quartz. All quartz is harder than glass. What's also cool about these particular samples is they illustrate how crystal form or hexagonal crystals are not cleavage. Because remember, cleavage is breaking in the same shape always. So here we have a quartz crystal that has 2, 4, 6 sides. It's a long hexagonal crystal, and it comes to a point, just like we think in our classic example of crystalline quartz. But here is quartz with absolutely no shape to it at all. Completely massive, completely shapeless, and this is milky quartz. They're the same thing, but you see that quartz doesn't always take the same shape, so it has no cleavage. Same thing with rose quartz. Again, it's this pink color because of a touch of iron in here, and maybe something else, but at least a little bit of that. But again, you see there's no defined shape to this. So quartz is harder than glass and has hardness of about 7. Non-metallic because it's not silver or gold in color, and no cleavage. All right. And our last couple minerals are part of the feldspar mineral family, and that is orthoclase, which is number 32, and plagioclase, which is number 33. What's similar about the feldspars is they both have two directions of cleavage that meet at 90 degrees. And that's easier to see on this particular sample of orthoclase, where you have one direction going left-right, one direction going front and back, and they meet, sorry about my snoring dog, at a 90-degree angle here. What you also see is these two sides are not perfectly parallel, not perfectly flat, don't really reflect light in the same way. So what differentiates orthoclase from plagioclase is something called striations, which I'll show you in just a second. So orthoclase is often this salmon color. It can be white as well, and orthoclase often has these growth lines on it. Growth lines are just that. They're as this mineral was cooling from a magma. But striations are these very distinct lines that are right in the side of a cleavage plane. So you won't see those lines. I hope this comes up on the film. You won't see those lines as I turn orthoclase over in the light. But when I take plagioclase and turn it over in the light, there are a series of lines go in this direction. And plagioclase is really the only mineral you have that has those striations. So feldspars, we have orthoclase feldspar, which they both have two directions of cleavage that meet at 90 degrees. And the orthoclase has no striations and plagioclase has striations. The only minerals, just to recap, that react to acid are calcite, which will react vigorously and right away, dolomite, which will react slowly and only when powdered. The only magnetic mineral you have is going to be magnetite. The minerals that are really distinctive for using the streak plate is limonite, which is has a yellow streak. Hematite has a red streak. And those are probably the most significant ones there. Hope this was helpful. If you have questions, please don't hesitate to ask them. Thanks.